Okay, that's everyone in. Good evening, ladies and gentlemen, members and guests. Our speaker this evening is Miles Franklin. Miles graduated from Imperial College London in 2011 with an M.Eng in Mechanical Engineering. Since then, he's acquired experience in a range of innovative projects, particularly technical solutions to energy and sustainable development challenges. His work has taken him to Sierra Leone, Malaysia, and China. Since 2016, Miles has been the lead engineer at Gravitricity, leading the engineering team for the development of Gravitricity's complex novel grid-scale energy storage technology. Miles is a chartered engineer and a member of the Institution of Mechanical Engineers. Ladies and gentlemen, Miles Franklin.
Hello, everyone. I will share my screen now and then start talking through some slides. I think I've just got one screen, so I won't see myself anymore. So if you just let me know, does that come through okay?
Yeah. If everybody could switch off their cameras so we can make the most of the bandwidth until we get to questions. Okay.
Perfect. I'll start going through then, and just give me a shout if the quality drops at all, and I can try switching to the internet that is available here. Perfect. So thank you, everyone. Nice to be here virtually. My internet is a bit dodgy because I am in deepest, darkest Devon. Gravitricity, though, we are normally based in Edinburgh. I've just come down to see my family. Just very high level to check we're all on the same page. Gravitricity is a company and a technology with the same name, developing a system for large-scale energy storage. So it's a mechanical system using electric winches to lift a weight in a underground vert. Lifting the weight transfers power from an electrical grid to the gravitational potential energy of the weight.
Miles, can I just check?
And then by lowering the weight again.
Miles, are you showing your slides? Because
oh yeah,
I still see your camera image.
Okay, that's good.
I think there's a green share screen button in the. That's great. That's it.
That's great.
Okay.
Okay, yeah. So we're not on slide. We can see the slides, but you need to press the slideshow button.
Perfect. Now can you see the full screen?
Absolutely perfect. Yep.
Okay, perfect. Sorry about that. Technical hitch. So what I was talking through was this slide here. As I was explaining, the technology is a grid-scale energy storage. We've got electric winches to lift a mass inside an underground vertical shaft, and by lifting that mass, we store, and then by lowering that mass with the electric winches running in reverse, the motors act as generators. We can then transfer that power back to the grid. So that's a starting place. That's what Gravitricity is focused on as a company, developing this concept into a kind of mature commercial technology. And so what I'm going to talk through today, just to give you a sort of little outline, is a very brief update, because I'm aware that I have given, or other members, anyone who has been in a talk before, just what's changed very briefly. Then probably in slightly longer than 60 seconds, but in not too much time, just sort of paint the picture of the energy storage world. Why do we care about energy storage? Why do other people care about energy storage? How does Gravitricity fit into that kind of big mega trend of energy storage globally? What do the full-scale systems perhaps look like? The Tower of Power, it's not what it's actually called, but just the 250 kilowatt demonstrator that we've recently built in Leith in Edinburgh. Talk you through a bit about that. And then what happens after that, what follows the demonstrator, and then a little tongue-in-cheek startup life. So I became aware that there's a sort of a lot of, you hear startup in the media a lot, and for a lot of us, we're very much inside that world. But maybe for some people, either at the beginning or the end of their careers, they may never have worked within a really early stage company. So I can talk just briefly about that as a sort of side note. So that's what we're going to talk through. So as part of that startup world, just to sort of bring you into the excitement of startup world, we are currently running a fundraise. So this is an equity crowd raise. I'll explain a bit more about how that works later on. But I took this screenshot just before this talk. I cheated a bit. It was as I was making these slides a couple hours ago. And we can come back at the end of the talk and see if we made any progress during this hour, and then hopefully you'll get a flavour for the excitement of being involved in one of these an early stage projects where we sort of live and die by the success of our ability to raise money. The kind of brief update since some of you might have seen the Gravitricity talk is we have significantly built our team. So we started last year with 4 full team members, and as of yesterday we have 11 full-time team members. There are a number of other people doing 1 day a week, finance guy, sort of technical advisor on the mechanical side, and various others. But the team has expanded a lot, and the big news for us is we've built this demonstrator. So we've gone through all those stages from paper drawings to CAD models through to a full 250 kilowatt demonstrator. That's a 12.5 meter tower in the Port of Leith in Edinburgh, and so this is a very exciting time for us as a team, as a company, that we have got to that stage. So that's just a little snapshot of sort of update. Now going really, why do we care about energy storage? It's clear that there are some very large kind of trends in energy in the current times, and those are about decarbonisation, they're about electrification, they're about decentralisation of generation, and all of these things mean that we need more flexibility in our grids, especially this sort of decarbonisation as we put more and more intermittent renewables into our grids. And energy storage is clearly one of the major sources of flexibility that allow us to operate our grids very stably, whilst having an imbalance of supply and demand in any moment. So because of that, different people have their different projections. Bloomberg has this one, that energy storage is becoming a bigger and bigger, and it is a sort of inherent truth that the kind of applications of energy storage are quite diverse. Fast response for a short period of time, and others that need interseasonal energy to kind of get us from sunny times to dark times. So the sort of range of technology solutions is expected to also be diverse to kind of fill this great big growing need. Below that, also what we focus on quite a lot is, alongside an increasing need for energy storage, there is also, in financial terms, a much bigger need for grid infrastructure to develop. So as the electrification of various different things like heat and transport increases, populations increase, and areas of the world develop, there is lots of money going into transmission and distribution grid. And I'll talk a bit more about that later on. Where does Gravitricity fit into this? You know, we've got a range of different energy storage technologies and solutions being developed all over the world. A way I sometimes think about this is that Gravitricity kind of has an aim to bring together some of the benefits of pumped hydro energy storage and of lithium-ion energy storage. So pumped hydro is still is still over 90% of the world's grid-connected energy storage, and that is largely because it once it's installed, it lasts for decades, and you can cycle it many hundreds of thousands of times without the performance of the system degrading. Clearly, there's maintenance and OPEX and these kind of things. On the other side of the spectrum, lithium-ion, which is being used more and more on grids, and with lots of positive media around that, has this real benefit being able to respond very fast. It's very dynamic and go from 0 to full power in very short, over very short durations. And so that makes it really valuable in the kind of frequency balancing markets, the sort of second by second balancing of the grid frequency that's becoming more and more important as we have more wind and solar and these kind of things on our grids. So we, as a kind of big mechanical system with very well understood components, with well understood mechanical maintenance requirements, are able to develop a system which has this long life, which can be cycled a large number of times. We can respond fast as well. So there's obviously design decisions in there which move the response one way or the other, and kind of the core kind of aim here. And the long cycle life is what enables a low levelized cost of storage, which is down here. So some work, I think it's going to be here, done by Imperial College, based a certain set of showed that under those conditions, a gravitricity system can be cheaper than lithium-ion in this levelized cost of storage, where a very large number of lifetime cycles has a great benefit in reducing the levelized cost of storage.
Miles, is your camera on?
Yeah.
Can you just...
Oh, yeah, my camera's on.
Uncheck the camera icon.
I'm going to... Hold on. Oh, there we are.
Okay.
Can you still see my screen?
We can see the screen. I just wondered whether, if your camera was on, it was we're getting most of the sound. How's that?
How's my voice quality now?
I think it might be better. Yeah.
If it's not so good, I can switch to that. Okay.
Let's push on.
Let me know in a minute if it's not so good. I can switch to the other internet and see if that's any better.
Okay.
Okay. So yeah, that's where we go. I think I'll there are some other benefits. I guess the other one maybe worth highlighting in the bottom right there is this idea that there's no standing losses. So once the system is charged, the weight is at a certain height, then the system until some point, or no loss of charge of the system until we decide to lower the weight again. And clearly no limits of how far the weight can go up and down the shaft. So that's kind of what's going on. Within all of this is the sort of more commonly understood version of that, which is what people call peak shaving. So here, this is implying some kind of industrial user that has is connected to a grid, and they here have got what they call behind the meter. And so by doing that, what they're doing is shifting a set of their demand to a different time period, and thereby reducing their peak demand user. That means probably a reduction in the tariffs they pay to their supplier. But the same concept could be used when developing distribution grids, where we're basically saying that the peak, classically developing distribution grids, the size for the peak demand required by some concentration of demand. However, if the grid is developed with storage inbuilt, we can then size for something much closer to the mean flows rather than the peak flows. And if we remember earlier on, we saw that the investment in energy in grid infrastructure annually is enormous. There's a massive benefit in reducing the scale of that grid infrastructure, and that is both in kind of developed grids in the UK, for instance, where we're increasing the capacity of those grids as we have more people and we have more electrification, but especially so in areas where we're developing new grids in the developing world for the first time, where those grids could maybe develop much more efficient than has been the kind of classical approach. Is that audio coming through all right at the moment?
Yes, I think it's okay. It's good.
Okay. Perfect. So a bit, not in super detail, but at around what full-scale systems kind of look like for a Gravitricity system. What we've talked about so far is on the left there. So this is a single weight system where effectively we have one large weight moving up and down in an underground shaft. It is, as a sort of example, if we had in a sort of typical UK mine shaft, a decommissioned UK mine shaft, would be about 750 meters deep. So in that shaft, if we would have a 500-ton weight, that would be a 1 megawatt hour system. And clearly, by doubling the mass there, our energy is mgh. By doubling the mass there, we could have double the energy capacity, 2 megawatt hours. Or if this was a shaft in South Africa rather than the UK, and it was 1,500 meters deep, then we could have double the energy capacity that way. And clearly, if you double both the mass and the height, then you have quadruple the energy capacity. So this is the sort of simplest configuration of a full-scale system. In that respect, we believe it's most suited to something like what lithium-ion is mostly used for in the grid, which is frequency balancing with quite a short duration of output. So, for instance, that example of a 1 megawatt hour system could be developed with a 4 megawatt. Did I say 1 megawatt? 1 megawatt hour energy capacity system could be developed with a power rating of 4 megawatts. So we've got a 4 to 1, and that's only a 15-minute output, but which is then valuable for these kind of frequency balancing services. Now, what we identified fairly early on in the development of Gravitricity technologies was that using a single weight is appropriate for that, but by moving to multiple weights, as you can see on the right here, we were able to scale for energy much more cost effectively. If you think about the single weight system, if you want to double the energy, for instance, in a fixed shaft, you have to double both the mass. So you're investing in double the mass, but also the capacity of the lifting system. However, as soon as you fix the lifting system and then in designing an ability to have multiple weights, then when you need to scale for energy, it's just about investing in more weights, which are the sort of dumb, stupid part of the system. So clearly there's a need at that point to invest in also the devices and the structures to support multiple weights. But this is the type of system that then is more suitable for tens of megawatt hours of energy storage, and is then more appropriate for this kind of peak shaving application. And when we tie all these things together, of the value of large, like a large cycle life with these kind of peak shaving applications, then a system like this starts to look very cost effective and valuable. In the other sort of big facet of full scale systems is obviously the shaft. So there's two obvious ways to think about it. One is use existing mine shafts, and there's a lot of them in the world, so that is a very sensible place to start. And the other way to think about it is to sink new shafts, specifically where some requirement is needed, which has some other factors about it. So for now, I'll just talk about the existing shafts, and at a kind of fairly high level. So we've done a lot of work over the last couple of years building relationships and projects with mine owners and operators and shaft sinking organizations around the world. These shown here are kind of the focus areas, and I'll talk a little bit more about just a couple of these now. So South Africa is really interesting because there is a lot of mining and a lot of very deep shafts, and also a weak electricity grid with a lot of issues with blackouts. And so a very interesting combination of characteristics for Gravitricity. We have an ongoing project at the moment, which has identified 35 specific 1,000 meter deep and over shafts, which could be suitable for Gravitricity installations. And we are working with a number of partners there to develop a couple of them as kind of early options for our first big underground system. So that's South Africa. It's interesting because there's a big need for energy storage and a lot of mining infrastructure. Czechia, or as it used to be called, Czech Republic, is also interesting, as are sort of neighboring countries. And this region is particularly interesting because there is a lot of mines currently closing. So the UK also has historically had a lot of mining. The Coal Authority in the UK has a record of 59,000 vertical mine shafts. But because these were closed longer ago, it's harder to access them and harder to find information on them. These shafts are closing right now, and there's a lot of interest and funding going into trying to find ways to reuse this infrastructure and repurpose it for new technologies. So we're working quite closely with a number of partners in the Czech Republic to kind of develop this proposition. And that's quite an exciting area. New shaft sinking, I'm not going to talk much about right now. It is something we have also worked on quite intensely. We're both with manufacturers of shaft sinking equipment. And so this, what you can see there, is made by a company called Herring Connect in Germany, but also with the contractors who who are kind of using these technologies and others to really understand what are the constraints and possibilities of various different shaft sinking technologies, and developing cost models for using those technologies in various different geologies. Our conclusion at the moment is that this kind of proposition of gravitricity systems in new shaft systems, in newly sunk shafts, is very viable. The cost of sinking shafts in these ways are less than seems to be most people's instinct. But so we are continuously developing that proposition, and as we kind of release more resource, now we've got through the Demonstrator project, we'll be looking at this more and more. So now to focus on the Demonstrator, which is really what we have been doing the most of recently, and is kind of our core focus. It is really a very exciting moment for us, having now having a physical system to play with and really test. For those who are interested in going to see it, it is down on the Port of Leith. You can't access it directly, I'm afraid, because it's the other side of the port gates. But the tower itself is where this apple is. So if you were to find yourself down in Leith and go to by the Fingal, which is the kind of hotel on boat here, and then either walk just past it and look across the dock, or there's some new housing over here. You find yourself near that housing and look across, then you can go and have a look at the Demonstrator. And if you're there in the day, you may well find it's going up and down. Now, I've got a video here which may be helpful based on our internet, but let's see. This is the Demonstrator just going up and down, so you can kind of get a sense of the pace. It's Steve and Francis having a little meeting in the sun. So you'll see that the pace going down is slightly faster than going up, because this would have been operated in this at this time to have the same power at the output of the system, so at the grid connection point. And when we're lifting, the losses through the system, the power losses through the system, have the result of lowering the speed of the weight. But when we're lowering, so we're charging back to the grid, in order to maintain 250 kilowatts at the output, we have to have a faster speed of the weight. So, at this level, it just goes up and down. It's perhaps not the most exciting, but clearly for us, there's a lot going on behind that, which is very exciting. So the Demonstrator, just a high level, what's it achieving for us? So one thing is we have these simulations of the full system, and we have a simulation of the Demonstrator. So we're obviously running the Demonstrator in parallel with those simulations, and as we're operating and identifying differences between the simulations and the full system, that offers us an opportunity to understand more about what's going on and dig a bit deeper there. So as we progress through the Demonstrator testing program, we will be refining those simulations, and then that gives us the perfect springboard to apply all of that learning to the full-scale system, where all of the dynamics are very similar. There are at some levels some new levels of complexity, but a lot of the learning can be translated across to help us understand and kind of refine our designs for full-scale systems. As part of that, there are some good technical challenges within this Demonstrator, and some of those are again translated through to the full-scale work. So, for instance, you can see just there running up the inside of the tower, there's two rails. along those rails, we have some guidance rollers, and some of the design behind that had some complexity in it on account of the loadings through the system and the various deflections and the results of the tolerances in the tower height, which in a shaft would be the tolerances in the shaft itself. So all of that can get carried through into full-scale systems. And I guess the next two there are sort of, as we, especially with the control system, are operating the system, we can dig deeper and deeper into the control system, and the variable speed drive, which is what operates the motors of the system, and play with the various parameters to understand where the real limits of the technology are, and sort of often forgotten, but as a team and as a company, the demonstrator is crucial for us to have a focus to build the team around, and then pull together all of our pre-existing experience, but then sort of collectively develop a new set of gravitricity specialist kind of knowledge and expertise, and then the demonstrators allows us to prove that the team has all these capabilities. So that's what the demonstrator is doing. Here again is another video. Let's see how it goes. I'll pause it and hopefully that will help. This is to sort of talk us through a few more different bits of the system. So this was the I'll go back a bit. This is the tower being installed. The tower is it's a kind of lattice structure that was actually fabricated off-site. It has two welded sides and then some bolted cross lacing, and that was then brought to site as a single piece and lowered down over the weights. A very exciting day, and the pause. You can see here we're lowering down onto a grillage. So this was a steel structure that we put on top of an existing concrete plinth on the Port of Leith. You can our technical director always says that with all engineering, the devil is in the detail. And my joke of the day, as I was writing this, I realized that with the demonstrator, the demon is in the demonstrator. You can see at the top here, and that was very much the case with the grillage here. It seemed like a simple part of the system, but in actual fact, there was the concrete plinth that was used for this system was installed in 1968 for a coal loading derrick crane that was used on the port for shifting coal, and all the load kind of levels were appropriate and suitable, but our civil engineering subcontractor spotted quite late that the load path was different in quite a subtle way through the slab, which meant that there was it was no longer competent. So we had to adjust the design of this white steel grillage quite late on in order to get that through. But we got there, and the system is up and running, so that's good. So yeah, the tower sits down on there. Now you can see this structure at the top is what we call the top frame. It has the sheaths or pulleys that the lifting cables run around. So the system has a continuous cable from there's two different winches. The cable runs up over here, down to the weights, and then back up round here, and then down to the next weight. Is the team expectant? The frame being installed is the tower. You can see the sheet up top. Now here you can see the two weights down at the bottom of the tower. So the weights themselves are each to 25 tons. So there's two 25-ton weights. You can see here there's a yellow sheave block, and in fact there's a link plate between the two. So what we will do is have two major phases of testing. During the first phase, this link plate is in place and the two weights operate as a single weight moving up and down. The continuous cable runs from from one winch, which is just kind of out of vision here, up and around the top frame, back, down to the weight, and up to the top frame, and then symmetrically on the other side. And then at a certain point, we will cut the cable in the center, put two new terminations on, and then remove the link plate, and then we'll be able to operate the two weights individually. And that will be a way that we can then start testing the control of multiple weights, and especially achieving a continuous output power from the whole system, whilst transferring the sort of generation effort from one weight and one winch to the other weight and the other winch. And so that will require us to move that yellow link plate and separate the two weights. One weight is called Isaac. Here's, sorry, it skipped. Here's the two winches. Yeah, you can see there's one winch. So it's a drum winch with a helical groove. In this case, it's a single layer, and there's two winches sitting side by side. Each winch is 125 kilowatt power rating, and so combined 250 kilowatts. I think the photographer thought those were the motors, but they're just the cooling motors. So there's the tower. So what have we achieved so far during the testing program? So far, we have gone through all of our commissioning tests. So here, top right, you can see George Brown, a very old Leith engineering firm, helping us witnessing our commissioning tests where we were applying an overload, a static overload. There's a set of other commissioning tests. So the sort of mechanical system is fully complete. There's a whole set of control safety systems in place that will need to be commissioned and tuned. That's what's happening bottom left here. We can see where sort of the system is moving towards a limit. The red line is the position of the weight. When we hit the purple limit, then the speed is ramped down to zero. So that's kind of safety system working effectively. We then, at this early stage, have also looked at, obviously, can we store power and put it back to the grid? And we've successfully achieved that and shown we can do that. So that's great. We had little doubt that it was possible, but good to do anyway. Variable output power, that's the fact that by the very nature of the system, we can output a continuous range of different output powers, which is very handy. Not all energy storage systems can do that. And we started to look at the speed of response. We haven't been tuning those, the sort of parameters that would affect that yet. So far, we have shown that in one of the different ramping scenarios, we can go from 0 to full power in under a second. For the others, we're slightly over a second, so there's some tuning required. And we showed that it's no surprise, but the power factor of the system is around 1, so we won't be causing any voltage issues on the grid. Next stages with testing for this demonstrator are looking more at speed of response and trying to tune the system to improve the speed of response, looking at the power losses and efficiency in both directions and round trip efficiency, looking at the power quality, so that's the harmonics of the system, how that affects the grid, and looking at how we can use the variable speed drive to dynamically change the power factor or the reactive power generated by the system, and then looking at this section of testing where we're moving the two different weights separately up and down and smoothing and blending that output to give interesting results. So that's all on the demonstrator. What happens after that is the next big project is the first big or underground project. That is a big a bundle of interesting technical challenges and will be expensive to implement. So, that's quite a long project. But the next big exciting milestone, and after that, obviously, we then move forward into some more kind of commercial projects. And obviously, as part of this big underground project, there may be a number of smaller kind of physical projects building up to that. I think it's unlikely to see there's one big leap from this demonstrator to a full-scale underground system. A little word on how we get to those big projects. Clearly, Gravitricity is a small company and a small team, and for if it was nothing more, would never be able to provide warranties for such large systems. So the vision is to scale with a industrial consortium. So we already work very closely with Houseman, who are a Dutch winch manufacturer who manufactures. In that picture, the Houseman commissioning engineers on site in Edinburgh a few weeks ago. And we are developing relationships with the other sort of blocks of this consortium to build together a set of sort of established benefit from Gravitricity projects developing. So then my little side note just on an early stage company, what it's like. So one of this crowd raise, I can make the link available. You can search it. You search progresses over the next 30 days. It's always quite exciting. And yeah, I guess that's one of the great characteristics is there's a sort of this common or semi-frequent existential need to raise money to push along, which can be very. There is a thrill to it, but it wouldn't be for everyone, I imagine. For those who all else. I think the other really interesting thing about an early stage company is that it is an opportunity to kind of develop a team, a working culture from scratch, which is very exciting. I don't know if looking at this picture, this is a technical team that is almost 50% women. In this picture, we have 5 women, 6 men. But that is just, I guess, one of the characteristics of the kind of the team and company and culture we're able to grow. And yeah, so far we have a very positive spirit in the company. The demonstrator was definitely, it was a stretch for the team. There was a lot. And always, as ever, problems with partners. But the team was always cohesive and sort of internally supported. So it was a very nice place to be. I guess some other little side points about startup. Every team member is critical to success. Here in this picture, we've got Julie in the middle there. She's our most junior team member, and during the demonstrator, had to pick up quite a lot of hot potatoes and keep them moving, and she did it very well. And then Stephen there next to her, 10 years more, obviously a different set of responsibilities through the demonstrator, but every member is critical, and every member ends up being involved in a lot of different challenges, both technical ones, non-technical ones. It's part of this crowdways we're running currently. There's PR challenges, there's website design challenge company. Everyone has to get their hands dirty, and it's always the case that there are some very big booming very close by, and so that, depending on personalities, can be quite exciting to be handed large problems. it can be intense. I guess that's the same for lots of industries and lots of different places of companies, but it's almost a given for startups, I would say. And obviously, as we're sort of saying, there's a need to raise money, and lots of startups fail. So it can be a bit unstable, but it can be a lot of fun as well. So that was my side note on startups, just based on an expectation that not everyone will have had the chance to experience it for themselves. So now I will just quickly go and see what the update is on the crowd raise. So when I was making these slides, just a couple hours ago, we were at this top one. So since then, around 80 new investors, and we've got about 20 grand more into the crowd raise. So that's very exciting. Today we've raised 74 grand. And the target for this raise, the minimum target for this raise was £750,000, and the absolute cap is 2.5 million. So we would aim to get up to around 2 million over the next few weeks. It will stay open for 30 days. So yeah, that's just another window into the things that are going on. So I hope the audio quality wasn't too bad and you managed to hear me. That's where I'm going to leave it.
Okay, Miles. Yeah, the sound improved after about 10, 15 minutes. So I think we've got all of that. So
Perfect.
Shall we stay on this screen? And I suggest that people either put their questions into the chat. If you click on the chat box, you can see questions that. So I think Bruce Davis started off with the first questions. Bruce, do you want to try reading your questions out, and then maybe other people could add their questions into the chat or speak?
Yeah, I'm always happy to have questions. You know me, Jonathan. I was wondering how the shaft size is affected by the mass you can drop down it, because if the shaft isn't big enough and you can't get the mass down it, that's a massive improvement, a problem. Secondly, could you get something from self-erecting tower cranes to help you put the structure up so you're not having to build it off site? And thirdly, where are the efficiency gains you're going to get if you're worried about it? For example, can you recover any energy from the thing stopping? There's lots of stuff in braking in Formula One cars to recover energy. Could you use some of that in your weight?
Okay. Well, a lot of questions. It was a bumper crop. So the first one, I think was sort of around weight, functional design. It's there's a sort of dynamic there. Shaft, then if you've got a fixed mass, for a fixed mass, the length of the weight gets very long. So in that example I gave earlier of a typical UK shaft being about 750 meters deep, then the shaft I'm thinking of there is a shaft in Yorkshire in the Rickle, the Selby colliery, and those shafts are 7.3 meters diameter. So they're in these kind of coal mine shafts. You're talking quite large diameter, and the weight itself then is not very, doesn't have to be very high to achieve this the target of, let's say, 500 tons. So you may be talking about 1-to-1 height to diameter type thing.
Okay, thanks.
If you were attempting to do things in So maybe I'll move on to the other one then. So then the self-erecting cranes thing, it's a good idea. Definitely the demonstrator for us is a sort of special case where we're doing anything above ground. We don't expect there to be a significant kind of opportunity in systems above ground. So whilst it's a nice idea, I think we don't really need to solve that challenge again. It was kind of a one-off for the demonstrator that we needed a big tower above.
You could invert it.
You mean to go underground?
Yeah. Build it from the top down instead of having to build a massive structure to lower it. You could build it as you go.
Yeah, that's true. And so in a way, so that the shaft sinking technology I showed, in a way does something like that. It's quite a clever system where they basically the cutter head is attached to the shaft lining, and you hold the shaft lining from above, and then as the shaft sinks, you add sections to the top of the shaft lining, and so the shaft lining is kind of extended down, adding sections from the top, and so then the lining itself kind of supports the cutting head. Because in a way, it's kind of a similar kind of idea.
Okay, shall we move on down the list? So Doug has got a question in the chat saying, can you comment on the aerodynamics, comparing the size of the weight against the size of the shaft? Shouldn't a demonstrator have airtight walls to closer model a shaft? So I guess.
So because we don't think it's significant. If you, again, using that 750 meter deep shaft, that weight so I was talking about a 500-ton weight and suggesting that maybe the system could be developed to have 4 megawatts of output, and I don't know the exact speed for that off my top of my head, but it will be somewhere between 0.5 meter and 1 meter, sort of 2.5 to 5 miles an hour or something. So the weight is moving slowly, and so any losses associated with aerodynamic drag are going to be pretty insignificant at that level.
Okay. So Matt asks, you touched on the cost of creating new shafts. What is the cost difference when compared to retrofitting a mine shaft? And how much does this impact on the LCOE?
Yeah, I mean, this is a great question. The challenges of this sort of reuse of existing mine shafts is the variability between the mine shafts and potential kind of big challenges in all coal mine infrastructure. There tends to be methane. In the UK, some of the shafts that were closed within the last 20 years or so, they've been capped, and that methane is so that's quite a good business. And in other shafts, that productivity of methane eventually drops off.
Yeah.
But then the shaft would not be being used for that purpose. In terms, it's quite low. It's still a kind of technical challenge to work out how to deal with that. So yeah, the costs and kind of challenges of refurbing mine shafts is a big piece of work for us. And I'm afraid, there's no simple answer on how the costs of the two compare. There's too many parameters in there.
Okay, kind of related. Who's Joe asks if you've considered, this is micro gravitricity. Have you considered small scale systems? There's a company, he gives an example in Edinburgh that services salmon farms and small isolated communities at the 10 to 50 kilowatt bottom end power level. could you store that in a small hole, presumably?
Yeah. I mean, it's clearly technically feasible. At the very small scale, there's even this company, I don't know if you've heard of them, called Gravity Light, that developed a kind of wall-mounted lowered. It was mainly for sort of low-income countries of rural communities. Small scale is clearly technically feasible, commercially sensible. So in those kind of scales, small portable lithium ion or other is probably more appropriate. I think the smallest that seems sensible is fairly shallow new sunk shafts for applications like electric bus fast charging stations in kind of remote areas, or even electric train remote fast charging at stations where you need high power, not the largest quantum of energy, but and it's quite difficult to, or it's very expensive to get that peak power delivered by the grid. And in there's some interesting cost models.
Okay. I don't think we're going to get through all these questions, so I'll just select two at random. Okay, two more. So there's one here asking what material the cables are made from and what's the factor of safety. Again, I would add to that, I guess the cables are the limiting factor in the whole thing. That, the mass, the size of mass that you can move, I guess depends on the cables and how many you have. Are they the critical component?
Yeah, so the cables used here are steel. There is definitely a move away from steel in some industries, especially kind of offshore lifting, where they're moving towards synthetic cables. For us, it doesn't seem there's the benefit for them is lightweight cables, but for us, we don't care. We quite like weight in this scenario. There is a bit more intricacy there that when all the cable is on the drum, that then the cable starts to increase the rotational inertia of the drum quite significantly, and which can affect the dynamics of the system. But steel definitely seems to be the way to go for us. There are, again, some interesting relationships around the selection of the cable. The kind of lifetime of the cable is determined primarily with steel cables by the number of bending cycles and the radius of that bend. And so you're looking to maintain a quite high ratio between the bending radius and the diameter of the cable. So here, if you look in this picture, we've got a cable and then a drum with a certain radius of that. And so you can reduce that ratio, but the cable life will decrease. And so, for instance, if you think about increasing the size of the mass, then the cable diameter needs to increase to maintain, for instance, equivalent factor of safety. But then the drums then need to increase the bending radius of the cable to maintain the life, and then you start to run out of space at the top of the shaft. Yeah. So there's some interesting dynamics through kind of those design choices.
Okay, and I'll merge. I hadn't thought of that actually. Yes, because the mass of the cables themselves and the drum.
Yeah.
And I'll merge. There's two or three questions that I think are all kind of driving at the same issue. I guess people asking about the maintenance needed for the shafts. So these holes go down a long way. They might not be dry. What are the costs of maintaining your shaft? Or is it that a factor, or is that something you've explored?
Yeah. So when it comes again here, there's a kind of split between new shafts and existing shafts. New shafts is a kind of much more easily bound question because you can kind of determine the conditions, and you're not going to have side entrances into to mine workings. So in the new shaft systems, it's quite easy to think about ways to put in remote inspection and such things, so you can kind of maintain the life without having to get in the way of the system operating or have people going underground. In existing shafts, again, yeah, it's a complicated question. There are different conditions in existing shafts. For instance, water is a good one, and which can be quite variable between different shafts. Some of the costs of that are quite easy to get a handle on, and some are more complex. We've done a couple of iterations through that, and feel that those costs, are manageable to kind of make a kind of a viable cost model. But over the next 6 months, we will be going back into them more deeply and trying to understand, exactly what's driving what, and are there certain types of existing shafts, with certain conditions that are just not viable.
Okay.
Yeah.
Thank you very much. So I think we've covered most of the bits. I'm sure if we didn't get a chance to get to your question, they could email you and get answers there. So I will pass to Kuhur, who's going to offer our thanks.
Yeah, thanks, Jonathan, and I hope you can all hear me. So I'd like to say on behalf of the committee and the members of IMechE and guests attending, big thanks to Miles for what was a very, very interesting talk. Let me say, first of all, whoever came up with the name of the company, what a genius. Gravitricity, does what it says on the tin. You don't need really to explain to anybody that knows anything about the world what that's about. And when I was listening to your presentation, it struck me very strongly that, if the gold standard for this type of grid scale energy storage is pumped hydro. Of course, pumped hydro uses nature to the advantage of gravity in nature, but of course we're limited by the number of sites that we can use in pumped hydro. And what really struck me was the comparison between the size of the challenge that we're facing in decarbonizing the way we live and the economy that we live in, and how crucial energy storage is for that increased electrification of our world, if you like, and how it's almost the inverse problem that the Victorians had. The Victorians were trying to generate power. You had the Industrial Revolution. And of course, this is what founded all of the great engineering institutions, such as the IMechE and the other engineering institutions. And it's very interesting that Gravitricity is actually using the old infrastructure of the Victorians to decarbonize the economy that they essentially carbonized. So there's some very nice kind of parallels and ironies involved in what you guys are doing. And, fantastic engineering. You've got this rapid response. You don't have to drop the weight too fast. You've got flexibility with multiple weights. And, I had no idea personally that there were so many disused mine shafts in the UK. I know they all won't be suitable, but it's very encouraging to hear you say that even if you have to sink new shafts, that it still could be cost effective. So that's very, very encouraging. I spent about 10 years in a startup myself, so sympathize very much with a lot of the things you spoke about, and I know you were concentrating on the positives. It's always good to concentrate on the positives. Of course, you're living from hand to mouth as well, and it was fantastic to see the diversity and the team culture as it builds up. And of course, we're very proud as Edinburgh and South East Scotland engineers that the Demonstrator that you talked about is being built and demonstrated here in Edinburgh. And as head of one of the schools of engineering, I hope that some of your team are graduates of either the University of Edinburgh or Heriot Watt. And finally, I'd just like to say that I think the crowdfunding idea is absolutely fantastic. I know that one of our other local companies, Orbital Marine Power, had a very successful crowdfunding where they raised £7 million to launch, and you'll have seen their most recent floating turbine, the O2, being towed up to Orkney for its first tests. I think it's a fantastic way of demonstrating, I think, the goodwill of large numbers of people for whom the individual investment isn't much, but they know that they're making a big impact by developing the technology. And I think it's a great way as well of spreading the message that engineering and engineering skills and technology can do a lot of good in the world. So I'd just like to say thanks. Your presentation was great, and I'm sure that the next few years are going to be very, very exciting for the company as everything scales up. And we hope that maybe you'll come back and present to us maybe in 4 or 5 years' time when everything has got all scaled up and you're further along on the journey. So thank you very much for your presentation, Miles.
Thank you. It was a wonderful summary.
Yeah, and maybe if we could unmute ourselves, we can do the traditional round of applause.
For anybody doing a startup, I did it as Jim and Jonathan did many years ago. And now I'm in my late 70s. I still remember the time, the difficulty, and the energy required.
So just before everyone leaves, let me put in a shameless plug for our AGM next week. So that's the last of our talks this year, which is, when we look back, the way we do these talks is transformed by coronavirus, but I think quite successfully. And we'll be doing some sort of hybrid program next year. So the AGM is on the evening of Wednesday, the 19th. I put the link in the chat so you can register and get the Zoom. From the membership, we'd love to get ideas for talks and visits, and especially if you have a contact. So we have a network of people, but obviously other people too. So if you've been inspired or you have an idea for somebody who could talk to us about an engineering related topic, we'd love to hear that. Same goes for visits. It'd be great to hopefully in September be able to go out and physically visit places again. And of course, most of all, we'd love to hear from IMechE members who would like to get involved. Volunteers to just attend these evenings, help us run the talks, but also, of course, to take part in the committee. We need a new treasurer. Our long-serving treasurer is moving on to help the Scottish region, and I know our secretary would love to be replaced. So, if you are interested, reach out, contact us. We can have a chat. I don't think any of these are onerous tasks, and it's a great way of building networks and making connections in the local engineering community. So Wednesday the 19th, 7 p.m. Please consider attending, and don't be shy. Have I forgotten anything, Paul? Is that?
Oh, that's everything covered.
Okay. So I think it just reminds us to say good evening, and hopefully see you next week.
Thanks a lot, guys.
Thank you.
Okay.
Thank you.
Miles.